All right, Andre, can you read off the question or read it out?
So I have a question about number 35.
From the homework.
The reaction is carbon monoxide gas plus chlorine gas. If we do a reaction to CO2. And the Kc for that is 1.2 minus 10 divided to the third power. That's 668 Kelvin. Okay, so you start off with 0.35 moles of carbon monoxide. And 0.055
.055?
Yeah.
All right, moles of COCl2.
Yeah.
And that's it?
And you find how many moles of chlorine gas is present in fluid?
All right.
This is a KC here or KP?
That's
KC. All right, so we just have to complete this ice table here. When we have gases, we have a choice. You know, if everything's a gas, we could either use KP or KC. So we just use the one that's easier for us. We need a volume though. Did they give us a volume?
Oh yeah, it's 3.05 liters.
3.05 liters?
Yeah.
3.050? How come they give us 4 sig figs here and then 2 here?
Oh, because it's 3500.
Oh, 3,500?
Yeah. And the same with the other one.
All right. 5,500. And then the chlorine, since they don't tell us the chlorine, it's going to be 0. There's no chlorine there to start with. And so the first thing is with the ice table, we're either going to work with pressures or concentrations, but not moles. So we have to convert these moles into molarity. That's probably going to be the easiest. So Churchy calls this the initial amount. It's fine. And then let's do the initial molarities. Initial molarities, we would take 0.35 divided by 3.05. Did you calculate the molarities?
No, I just left it as a fraction.
Okay, let's go ahead and calculate the number.
Because it cancels out when you do the equilibrium.
It's not going to cancel out because we're going to have molar on top and molar squared on the bottom. So yeah, it doesn't cancel. When it does cancel out, like you get molar squared on top and molar squared on the bottom, then we can use moles. But in this case, we cannot use moles, otherwise the volume won't cancel out. And so we have to actually punch in and determine the molarities for each of these.
One point
1.147, and then I need one more digit. Because, what is it? 75?
Yeah.
Okay, molar. This will be 0 molar, and then this would be
Oh, it's times 10 to the negative, so it's just 0.1147.
0.1147. Okay, that's good. Times 10 to the negative 2.
Yeah. So it would be
Give me one more digit. Like 1083. 2. All right. So we calculate the molarities, and then we figure out what direction the change is going to be in. Here we don't need to do Q calculation because I see a 0. If you see a 0, the direction is going to be in that towards the 0. So this is going to be plus x molar, minus x molar. All these are 1-to-1 ratios. And so at equilibrium, we're going to have 0.11475 plus x molar, and then x molar here, and then 0.01082 minus x molar here. Okay, we plug this into the Kc expression, which is just the concentration of CaCl2 divided by CO and Cl2 concentrations. And then we'll just plug in the expressions here. 0.010832 and 83.2 minus x divided by 0.1147, so 5 plus x times x. In this case, you can see here that the products are going to be biased, but we can't reset this. I mean, I guess we could reset it. We could reset this all the way to the left. But if we reset this to the left, then we're getting farther away from this, and the change is going to be bigger, and we're still left with two binomials. And so in this particular case, you know, the math isn't too bad here, because this is just going to be a quadratic. We could try the simplifying assumption, you know, and say that x is going to be small compared to these. See if that works. You want to try that, or just go ahead and solve it? Okay, let's go ahead and give it a shot. You know, this is product bias. It's not hugely biased, but good. So we'll try the simplifying assumption. That's going to bring this to 1083. So 2 at the top. On the bottom, this is going to be 1147.5, and then x. Solve for x. Okay, this is with the simplifying assumption. We're going to say that x is much smaller. Well, which one's a bigger percent change? Well, it's got to be this. And so x is going to be much smaller than 0.01083, so 2. As our simplifying assumption. So what does x come out to? Well, just punch this in your calculator. 0.01083.2 divided by 0.11475 divided by 1.2 times 10 to the third. What do you get? 8.097 times 10 to the negative 6. We're only allowed 2 sixties. All right, now we have to justify the simplifying assumption. And so we're going to say that the percent change is going to be the change, 0.01083. Oh, actually, that's not it. This is the change here. The change is going to be 8.067 times 10 to the minus 6.
Professor?
Uh-huh.
It's 8.097.
Oh, okay, 8.097, thanks. Over the smaller original, 0.01083. So 2 times 100%. What does that give you? 0.07%, which is okay. 0.07%, I can feel comfortable. If it's getting higher and higher, like 3%, 4%, I start to feel uncomfortable. And I say, maybe I'll just use a quadratic equation, or maybe I'll just solve it. rather than making this assumption. All right, and then we go back over here and we just recalculate all the concentrations. So this is going to be 0.11475 plus x. So x is going to have, let's 10 to the minus 6, so we need 5 zeros. 1, 2, 3, 4, 5. And then it's going to be an 8097. So 8097. So we add it together. We got 0.1147 sub 508097. It really didn't change things much, did it? And so then you know the simplifying assumption is pretty good here. Didn't change. And then the chlorine is going to be 8.097 times 10 to the minus 6 molar. And then the COCl2 is going to be 0.01083 minus 0.50, and then 8097. So we're going to carry some extra zeros here. It's going to give me 2, 0, 9, 3, 2, 8, 0, 1, 0. And so we lose a little bit. We start off with 10, 8, 3, 2, and we end up with 10, 8, 2, 3, 9. Just a little bit of loss. All right, the next thing is, well, I don't know, can I trust that calculation there? Well, we can always double check this. How do we double check the answer? We just multiply the concentrations here at C. Does it give us 1.2 times 10 to the third? And so for our double check, we'll just take this divided by this divided by that. Can somebody do that? Let's see what we get. Someone have it? Just punch out 0.010823. We carry extra digits to avoid round off there. 3902. Then divide by 8.097 times 10 to the minus 6. Divide 0.1147508097. What does it come out to? What did you get? 1.6 times 10 to the third?
No, 11.6.
11.6 times 10 to the third? All right. If you see something like this, it's supposed to equal 1.2 times 10 to the third, and we get 11.6 times 10 to the third. Do you think that's due to round-off error? No, this is a huge difference here. And so there must be some error, some other error here. And so the double check is, well, we have to go find that error. Where was the mistake made, because this is not a match. And so we go back and we double check our calculations and the numbers. to make sure that it's right. And so I double check the X calculation to make sure that looks good. Uh-huh. Oh, you got a different answer for the molarity? Or what did you get? Well, that, you know, even if this is wrong, we could have made a wrong answer here. But then that means there are two errors. We still have an error here. Because with the wrong initial, it should have given us a K that matched because we used the wrong initial to solve for X. Right? And so let's first find the error here, you know, assuming that, well, we didn't make a mistake with this concentration.
So there's no error in that calculation.
This calculation is good?
Yeah.
Okay. Then we take a look at this. That looks okay. This looks okay here. That looks okay there. Okay, then we recalculate our K, just make sure. You know, when I see something like this, sometimes I think of this as an exponential error. I don't know about if Twee, this happens to you sometimes or not. Well, usually when I have scientific notation, I notice that people are always off by a factor of 10 because they're just not familiar with the calculator. They don't know how to plug in scientific notation. Sometimes this happens. And so I find this happens commonly with people who do something like 8.097 and then they hit the times button and then they type in 10 and then they raise that to that power. You know, sometimes that doesn't work right, but I don't know if that is it.
The molarity for the product is wrong.
Yeah, this molarity here, yeah. Okay, this molarity is wrong, but still, even with the wrong molarity, you know, because we use the wrong molarity in this calculation, so there's another error. There's two errors. You know. There's an error in the molarity, and there's another error. So let's find the other error fixed first, and then we'll fix the molarity error.
Can we do it without actually having to divide it? So we just have a fraction like
No. You could. I mean, it's just.
So that way we can avoid having error.
You could in rare problems, but it's not worth it. You just do it. You divide it. It'll make your life easier. If you start putting in fractions, you're going to have a headache because the x also, you know, the x also has to have a fraction.
Yeah.
And so the x is going to be x over 3.050. And then you get fractions in your binomials and you're multiplying those out. And it becomes a big headache. Unless they cancel. If they cancel, that's good. But in this problem, they don't cancel. The fraction. Yeah.
And then from there, I just got the easy numbers from the bullets.
Okay.
Yeah.
All right.
So would that work?
That would work. Yeah. If you can solve it like that. Well, anyway, the error is somewhere between here and here, and I didn't bring my calculator. I'm going to stop the video right now, and I'm going to calculate.